Students, today we'll discuss some properties of nucleus. We are starting the nuclear properties. So first of all these elementary properties of nucleus, you already, everyone, all of you know that. So let us have a very quick look on the properties of the nucleus. We are usually accustomed to do when start with any bound system. First of all, the binding energy. So this is delta M, also called mass defect. So this is delta M. M, it is AZ, mass of AZ, and minus A, where A is the mass number and is the atomic mass. So this is the first, wherever we have a bound system, the first property we ask about that how strongly bound in the system, and that gives us the idea if we know the binding energy of the system. So this is very important property when we study any binding system. Secondly, another point is the packing fraction, which is defined as the delta M by M. This also gives information about the bound system. So when a nucleus, when the proton and neutron, these nucleons are bound together, so packing fraction is also a very important experimental thing which we can use for deduce our theoretical ideas or theoretical models. Next, nuclear volume. So volume is supposed to be proportional to A, where A is the mass number. So if we can consider a radius kind of thing for a nucleus, so volume will be like in this 4 by 3 pi r cube. So if we just put it as R, I mean proportion equal to A approximately, in that case R will be proportional to 1/3 of the mass number. So in that case, R can be written as R0 A to the power 1/3. So here we have the very important, very simple but important relation between the radius and the mass number of the nucleus itself, where R0 is a parameter which is called, we call it a radius parameter. So nuclear radius parameter is also very important thing. So if we have the idea of atomic mass, we can have the idea of what will be the possible radius of the nucleus. Or from this expression, if we consider you are given radius of two nucleus, considering R0 to be the same for the all nucleus, you can find out the ratio of the atomic numbers, or if atomic numbers is given, you can find out the ratio of the radius of this of the two nucleons, and if one radius is known, we can find out the radius of the other nucleon. So this simple relation gives us a way to get an idea of what could be the possible radius of the nucleus. Now, third important point is nuclear spin. So we know the component of nucleus is proton and neutron, and proton and neutron, they are Dirac particles, and they have the intrinsic spin, which we call a half H curve. Now, nucleons also possess quantile orbital angular momentum about the center of nucleus. So if you can consider there is a center of mass inside the nucleus, although its idea is a little bit difficult, but till if we can consider there is a center of mass inside the nucleus, so in that case we can consider a kind of orbital angular momentum, and the total resultant angular momentum J, we know that it will be L plus S, where S is the spin and L is the orbital angular momentum. Now, according to the prescription of quantum mechanics, we know that the total angular spin angular momentum can be represented by this, and this is very well known to you, nothing new about it. Now, when we come to the case of our nucleus, in that case, the resultant spin angular momentum will be obtained by the vector addition of the spins of the individual nucleons. So this is a very simplified picture. But we consider that the total spin angular momentum will be the summation of the spin of all component nucleons. And similarly, the total orbital angular momentum L, that will be summation of the all component angular momentum of all component of the nucleus, that is proton and neutron. Now, since S is half, here we have a very interesting observation. That is, since S is half, S can be either integral or half integral depending upon the number of nucleon presence inside the nucleus. So, if we get as a whole, we get the spin of the spin angular momentum for nucleus. It can be even or odd. From that even and odd of spin, we can at least say whether there is even number of nucleons inside the nucleus or odd number of nucleons inside the nucleus. But total angular momentum is 0, 1, 2, or as usual we consider. So these are the initial properties we study about the nucleus when we start to go discuss the properties of the nucleus. The next things come is the magnetic moment, dipole magnetic moment of nuclei. So due to the spin and angular momentum, both we know that there exists magnetic moment. So proton and neutron are has the intrinsic magnetic moment and related to their intrinsic spin. Now the spin angular momentum, we know that, let it be represented for proton pp, so this will be sp, that is the spin h card, and for neutron it is again, we call it the spin quantum number s and h card. But for neutron and proton, we know that they are values of half, so the it will be both the cases, it will be half h cards. Now the ratio of magnetic moment to the angular momentum. Suppose this is the magnetic moment mu p and we have the spin angular momentum. So this will be Gp E by twice Np. E by twice Np, this is the Bohr magneton. We know that, we put it as mu n. And Gp is the Landis splitting factor. So this is very, very important parameter or important quantity. So from the idea, if you get an idea of Gp, that is Landis splitting factor, in that case we can find out, we can have an idea about the energy states of the nucleus as a whole. So this is for proton, and if we consider the neutron, we put it at Gn. So Gn and Gp, for Gp is this. So let us the ratio of magnetic moment for the neutron and the spin angular momentum be Gn EMP by 2. So EMP by 2 is the nuclear magneton we have discussed earlier in the context of our discussion of deuteron. So from these two expression we can come UP will be Gp SP H card twice NP. So Gp by 2 mu n. And similarly for neutron you get Gn by 2 nuclear magneton. And here you see I have written this Gp and Gl Landis splitting factor, which is a very important quantity. If you forget about the Landis splitting factor, please go to the Zeeman effect, particularly anomalous Zeeman effect. It is related to the L and S and J of the system, which is nothing but the angular momentums of the system. In other words, this represents the energy states of the system. So Gp and Gn, the splitting factor, is a very, very important quantity. Now for proton, it is found to be these values, and for neutron, it is having this value minus of 1.1931. So just look at the minus sign. This is also very interesting and important point to be noted. Now, if you write in a vector form, we can write it like this: sigma p sigma n. Why? Usually that is the Pauli spin operators, the conventional way of writing. Now, when we read all these properties of a nucleon, so some very important information can be derived from these experimental observations or our magnetic moment, binding energy, etc. So what are the important notes? So it must be carefully studied. Proton is positively charged, and direction of mu p, that is magnetic moment due to intrinsic spin, is the same as the spin angular momentum. So it is Landis splitting factor is positive. Negative sign of Gn, that is Landis splitting factor for neutron, indicates that mu n is directed opposite to the Pn, that is spin angular momentum. This is very important. The orbital motion of proton produced electric current, which is the source of magnetic property of nucleus, right? This is about the orbital motion of the proton. We'll discuss later, little bit later. Now, neutron being neutral particle should not expected to possess magnetic moment. We know that the magnetic moment usually exists for the charged particle. That is, when you place a charged particle in a magnetic field, it has some splitting in the spectral line. It changes its energy, it deflects, it changes its direction, and everything we have written in our we have read in our undergraduate classes in case of Zeeman effect. So it is not expected to, sorry, it should be not, it should not be expected to have some magnetic moment, but neutron has some magnetic moment. Experiment says that. So the value is called the anomalous magnetic moment. This anomalous value can be understood by meson theory. So we'll discuss this later when we discuss the elementary part, neutron as an elementary particle, or the complex particle, whatever. So this is about the magnetic moment due to the intrinsic spin. So for complex nucleus, intrinsic magnetic moments of all protons and neutrons are vectorically added. So in this simplified picture, we just add all mu for proton and all magnetic moment for neutrons. Now the orbital angular momentum also have contribution to the, of course it has contribution to the magnetic moment, and the resultant orbital magnetic moment for proton can be just as our similar way we can write like this, as in previous work, where PL is LH card, where L is the orbital angular momentum, and it is the Bohr magneton. Sorry, it is the nuclear magneton. So the orbital motion of proton GL is found to be 1. So mu L will be L into mu N. So the contribution from neutron will for orbital motion will be equal to 0. It is a neutral particle. So when we now at the end of the discussion, we come to the what will be the resultant magnetic moment for due to its orbital motion and due to its spin will be just vector summation of all these three quantities. So it is mu pi summation mu ni if the nucleus has the I number of nucleons, and it is a pi, and that is due to the, and here we have considered the proton and neutron are have the same number. We consider a nucleus where the neutron and protons may have the same number. So if it is otherwise, you can write some I means it may be different. You can put it a different way. So it may be J like this. So this is about the total resultant magnetic momentum. And the spin operator, I have written it separately in case you forgot it. So these are the three spin operator. We must remember, any student of physics must remember very sharply. So anytime if you are asked what is the Pauli spin operators, that's why I have written today. So this is about the nuclear properties. In our next lecture, we will discuss about the what is the forces of nucleus, the nature of the force of the nucleus.